Hi everyone, welcome back. This week we're going to talk about inferential statistics as opposed to descriptive statistics, which we covered last week. And there's an important relationship between descriptive statistics and inferential statistics, but we're going to start to make a leap from talking about samples to talking about populations. So in part one today, we're going to talk about sampling and parameter estimation, which we're able to do from our descriptive studies. Descriptive statistics are used for describing samples. Okay, so far we've looked at not only samples, we've looked at really small samples of data and calculating some basic statistics like means, medians, and modes. And even if we had a slightly more robust data set, we're still talking about a sample. And our goal as researchers, don't forget, is to create generalizable knowledge. We aren't just interested in who's in our data set. We want to be able to often say something about a much larger population. So if we're doing a clinical trial, we're not just interested in the patients that we treat. We want to know what would happen in the population in terms of efficacy if we were to introduce that into the population. So we're going to use inferential statistics for coming to conclusions about what is probably true in a larger population. Notice I said probably true because within statistics, we always have to allow for the fact that we are potentially making some amount of error. And sometimes we can't even quantify how much error we're making. But we try to develop methodologies that minimize the amount of error that we introduce into our inferences. So we're going to take samples from a population and make inferences. Inferential statistics uses the laws of probability to provide guidance on what is probably true in the population. So recalling again that the goal of research is to create generalizable knowledge. And so to be generalizable, our data, first of all, has to be sampled in such a manner that it is representative of the population from which it's drawn. And normally what we do is what's called a simple random sample, where we randomly select participants to participate in the study. Now, there's often deviations from that, but the inferential statistics that we learn in this class are based on primarily simple random samples or possibly stratified random samples, but that doesn't always occur, although ideally it would. Inferential statistics are used by researchers to make that leap from descriptive statistics to making claims about what is true in the population. Samples must be sufficiently large, representative, and randomly sampled to provide valid estimates of population parameters. And I've used this term parameters, and that's specific to populations, as we'll see here in a moment. So let's think about a population versus a sample. A population is something we don't know everything about, right? That's why we do a study. We don't have access to information on everyone that we're interested in, let's say, who have a specific disease or receive a specific intervention. And so we take a sample, we draw a sample from that larger population, and then by summarizing that first with descriptive statistics, as long as it's representative of that larger population, then we can make inferences about that population using inferential statistics. So a lot of the work here comes into the study design phase where we make sure that our samples are representative. Otherwise, we may be making inferences about a very select population or a population that we didn't intend to make inferences about. So especially if our goal is to estimate, let's say, prevalence of disease in the population or something that actually would be published as being what we know about a specific phenomenon, we want to make sure that we do a good job in the study design phase, and statistics can only help us out so much as far as doing that. But if we've done proper sampling techniques and they're randomly sampled, we should be able to make actually really good guesses or inferences about what's happening in the population. So some examples of populations. Populations might be something like all people in the US with asthma. Okay. So a population doesn't mean always the population in the United States or the population of some state or something like that. In fact, normally it would be something else, something that's specific, something that we're interested in for doing research among a certain group or maybe a certain subpopulation. So it doesn't have to be the whole population. Women ages 18 to 44 who are pregnant could be a population of interest. all high school age adolescents with a substance use disorder, patients of all ages with newly diagnosed pancreatic cancer. Okay, so these are not research questions, but they're examples of populations for which we may conduct research studies and want to make some inferences about treatment effects, about the epidemiology, course of illness, things like that. So these are examples of populations. Now we don't, again, have access to information on all of these individuals. And if we did, we wouldn't really need inferential statistics. We would just be able to describe the population. But what we do instead is draw samples, and from that we make inferences. And we can do a really good job of this. So examples of a sample would be a randomly selected cohort of patients with newly diagnosed asthma selected from outpatient clinics. Okay, so if we're trying to talk about the experience of asthmatic patients, ideally we're going to randomly select patients newly diagnosed, not necessarily ones who have had it for a very long time, because there can be what's called a selection bias or a survivor bias that would make them not representative of the entire population of patients. So really we're going to focus on these newly diagnosed asthma patients for this particular study. Pregnant women who appear at an OBGYN clinic during weeks 12 to 18 of pregnancy. Okay, so this might miss some, right? It's going to miss people who don't report to an OBGYN clinic, maybe people who use midwives or do at-home births, but more often than not, they're going to have a visit to a doctor, an OBGYN doctor. And so, yeah, we may miss some people. And so we have to adjust the population that we're generalizing to, which is typical pregnancy where there's care received during sometime in the first or second trimester. We can also have a cluster sample of US high school students enrolled in 10th through 12th grades in 17 United States. So though it's not all the states, we might do a systematic sample. Let's say we have a certain number in the West, a certain amount in the East, a certain amount in the Midwest, et cetera. And we're going to take students enrolled in 10th to 12th grades and do some kind of survey. This is how actually the Youth Risk Behavior Survey is done nationally, to find out how many kids are using certain drugs or bullying or other things like that. So that's how we know what we know about those populations. Is it perfect? No, because there's going to be kids who aren't enrolled in school at all. There'll be kids who are not enrolled in school that or at school that day. We know there's going to be certain limitations, but that's how we sample things often. We try to get as close to that population that we're interested in as possible. A registry of pancreatic cancer patients who have agreed to participate in clinical trials. I'm guessing you could already see a potential bias and why this would not be representative of everyone, but that's probably the best we can do, the closest we can come to talking about the patients who would reasonably seek care and also probably are likely to want to take specific drugs, especially a new drug. So it is representative of a population of patients who are willing to receive, treatments, especially something like pancreatic cancer, where we need novel treatments to improve outcomes. So those are examples of populations and samples. And samples are always going to be a little bit different from the population that we're actually interested in, just because of either practical concerns or just our ability to get information or to get participants. But our goal is to say something about those larger populations. So I want to distinguish between a statistic and a parameter. A statistic is used to describe a sample. We've already calculated some statistics. We calculated a mean, we calculated a median, and a mode. Those are all examples of statistics. The R, Pearson's R correlation coefficient, okay? We use those to describe a sample, not a population. A parameter is a population value that we estimate using sample data. So we're able to go from our statistics or our samples to a population, but that's what we're trying to estimate. It's an unknown parameter, okay? And ultimately unknowable in the sense that we don't have a full census of information from that population, okay? When I say census, if you think about a census, it has theoretically everyone included in it. And so it describes fully a population. In health research in particular, we're not going to have that kind of access. We have a very fractured healthcare delivery system. When we talk about something like mental health, it's even more fractured. And so you're never going to get the whole population. And there's going to be different data sources and different ways of approaching these questions. So it's particularly hard in the United States to get information on the whole population anyway. But even if we were able to have access to all that information, often we're trying to say something not just about a point in time, but people in general. So even if we had all the data of everyone currently in the United States, we could be thinking about generalizing to a larger population of future US population, for example. We use inferential statistics along with sample-based estimates to say something about a population. And a certain amount of skepticism is probably already creeping in here and saying, well, we don't have all the information. How can we do this? Well, we can do it pretty darn well. And we'll give you some examples of where statisticians have gotten it right and statisticians have gotten it wrong. But we really have developed methodologies that assure that over the long haul anyway, we're not likely to make too bad of an inference. And if we do, it'll be replaced with other information over time. No one study is definitive. So we want to make sure that we keep that in mind as well. So when we talk about parameter estimation, we never have an exact quantity for the population like we do with a mean, where it represents actually the mean in our sample. Parameter estimation is used to estimate a population value using our sample data. So a sample mean, a sample percentage or proportion, we might calculate a relative risk or an odds ratio. And the parameter can then be both a point estimate, so any of those measures I just mentioned, the population mean, the population relative risk, the population proportion, or an interval estimate, a range of values that we think might be true of a population. So what proportion of the population currently has asthma? Well, our guess might be like between 8 and 10%. That would be an interval estimate. So a point estimate involves the calculation of a single value as the estimate of a parameter. Okay. So a point estimate really is simply the value of the descriptive statistics from our sample, assuming that we've randomly selected from that population, and our goal is to say something about a larger population. So a sample mean or a sample proportion. But we need to also then take into account that might not be exactly the true population parameter. We're making an estimate, and we should use language and measures that kind of quantify that uncertainty. Okay, some examples of point estimates would be, we might say something like, in the United States, the average lifetime risk of pancreatic cancer is about 1 in 64. That's over the entire lifetime. Okay, and that's the actual value from the American Cancer Society. Well, where did they get that number? It's based on sample data or registries of patients known, and we can then make estimates about risk. Approximately 25 million Americans have asthma, including 8% of adults and 7% of children. These would be examples of point estimates. In this case, we have two subpopulations, adults and children, and we have a count, an estimate of the number of Americans who have asthma. Again, this would be based on samples and other techniques to get our best guess as to what's happening in the population. Usually it's not from a single study, usually it's from multiple. The median age of onset of schizophrenia is 25. Okay, so that's another example of a point estimate where we take a single value to describe what's happening in the population. Interval estimates are those that provide a range of values within which the population value has a specific probability of falling. Okay, we want to make it clear that when we come up with a point estimate, there's going to be some boundaries or a margin of error around that we can calculate. Right? And though we may have made a mistake and we may be off, we know we can calculate to what degree we would likely be off. So interval estimation involves constructing confidence intervals or margins of error around those point estimates. And as we'll see, as we get bigger and bigger samples, the narrower those confidence limits becomes. If we have really small samples, our confidence limits will become much wider. We're not going to be as confident in data that's from a small data source compared to when it's much larger, and both would have to be representative to be valid to begin with. So an example of interval estimates would be people who smoke cigarettes are 15 to 30 times more likely to get lung cancer or die from lung cancer than people who do not smoke. Okay, there's a range of risk estimates. And so this is an example of where instead of expressing it as a single value, we're saying where is the range of values. We're talking about a certain amount of uncertainty from the data sources we have. We know it's not zero additional risk. It's somewhere between 15 and 30 times the risk. For people who inject drugs, the risk of HIV transmission per injection from a contaminated needle has been estimated to be between 0.7% and 0.8%. May sound like relatively low risk, but that's per injection. And if somebody's a daily user, then you can start to multiply those the chances of not getting HIV, and over time it becomes a much higher probability. But in this case, that would be a population parameter estimate expressed as a fairly narrow range. And this is based on multiple studies, but a single study could come up with an estimate as well, as long as it was large enough. So when we use inferential statistics to estimate a population parameter, we must also account for the uncertainty around that parameter estimate. Okay, so we don't want to state as fact that X% of the population has this. It's better often to have some kind of confidence interval around that estimate. And if you look at the research literature, you'll often see a point estimate and a confidence interval. Usually it's a 95% confidence interval, which we'll talk about. But that's what that range of values is. And it's derived using inferential statistics methods. Okay, so it puts boundaries around where a population value is likely to fall given our data. And again, if our data set's relatively small, a relatively small sample, we have a fairly wide confidence interval. If we have a much larger sample, we have a more narrow confidence interval. We're going to get closer and closer and closer to the truth. By convention, we often use 95% confidence intervals, which means that the probability is 95% that that range of values that we present includes the true population parameter. It doesn't say where it falls in that range. There's a lower bound and upper bound, and we're saying we're 95% confident the true population value falls within that range. When we say we're 95% confident, that means there's a 5% chance that it doesn't actually fall in that range. But that's the risk that we take as statisticians in making inferences to a population. We do allow for possibility of making a mistake. Thankfully, science is self-correcting, and hopefully there'll be another study that will also attempt to estimate the same parameter. It can correct over time anything that was erroneous. So we, again, don't usually rely on a single study to make decisions in public health settings or medical settings. As I mentioned earlier, inferential statistics and random sampling go together. We expect our samples to be random and independent for the most part. What that means is we're not repeating observations on the same people. We're not taking family members from the same household just because it's convenient. Okay, and there are statistical ways to account for those kinds of deviations from random sampling. And we'll talk about a few techniques that are relatively common and that are by design. But much of our statistical inferences are based on using random sampling. When we draw random samples from a population, they may be different from the true population just by chance alone, right? So if I take 10 people randomly off the street, okay, if I'm walking down the street, take 10 people randomly and I ask them if they are right and left-handed, I might get 10 right-handed people, and my inference would be that 100% of people are right-handed. Well, we know that's not right, or correct. So, well, if I took 100 people, it's gonna be a long afternoon, randomly selecting 100 people off the street, I might find that 15% of my 100 are left-handed, or whatever the true population parameter is. And if I were to do 1,000, 10,000, et cetera, I'm going to get closer and closer and closer to what the real percentage of people who are left-handed. I can account for maybe some don't even know, or they're lying and all that. That's fine. But we can still, with a large sample, get pretty darn close to the truth. Okay, so as samples become larger relative to a population, they help to minimize the risk of obtaining a parameter estimate by chance alone. Okay, this idea of by chance alone is a really important statistical concept, because there is going to be that issue whenever we draw a sample that it could differ randomly from, or may just by chance alone differ from the population. So here's an example of a difference between what I'm talking about in terms of random sampling error versus systematic error or systematic bias. So if we have a registry of pancreatic cancer patients who agreed to participate in clinical trials, okay, a systematic bias here, which you probably already figured out, is that we're going to miss patients who do not present to a clinic or do not agree to participate in research. Okay, it's a very fast course disease. There are people who will never report. They may never have the opportunity to be a part of a registry. So we're going to maybe have a slightly skewed population as far as who's in our sample. That's systematic. That's how we went about drawing the sample, and that's going to introduce a certain amount of bias. Sampling error is that by chance alone, a sample of 200 patients may overrepresent or underrepresent certain types of patients. Okay, if we only have 200 patients out of 200,000 patients, just by chance, we might not get as close as we want to the truth. But if we had a much larger sample, or even a modestly larger sample, our risk of making an erroneous inference becomes much, much less. So I talked about random sampling, and the sampling design is an important step in the research methods. Often biostatisticians are consulted on research methods or are very instrumental in deciding on research methods, but statisticians aren't always there at the beginning, and sometimes they have to clean up the work that's been done by others. But that's not ideal. Ideally, a biostatistician would evolve from the very beginning to talk about measurement, how things are going to be measured, how many categories there'll be for categorical variables, et cetera, so that you can develop a full analysis plan based on that methodology. So researchers must often make trade-offs in terms of the cost to obtain their data and to enroll participants, and any potential biases and the level of statistical power that they'll have to make inferences. So if it's really costly to get participants to participate, whether it's through incentives or just the time of follow-up or just the amount of research personnel that are involved, then they may have to have a slightly smaller sample, but they might have to then make some other trade-offs in terms of making sure that they have a truly random sample, okay, or other things that will make their study sample more close to the truth. Ideally, studies will use some form of random sampling, but advanced statistical methods do allow for other sampling methods. For example, there are certain health conditions where it may be very hard to get participation. Okay, I already mentioned IV drug use, right? So it may be hard to get a purely random sample of people who inject drugs. So there's other sampling methods. One's called snowball sampling, where one person refers to another person who refers to another person, clearly not a random sample. And we are developing novel statistical techniques to deal with those kinds of non-random sample. But the statistics that we learn in this course are based, for the most part, on random samples. So a simple random sample The goal is to be representative of the population from which it was drawn. So we're going to give an even chance to every individual who has a disease, if that's what we're interested in, or if we're just interested in the general population, every person who meets our criteria for being in the study, they're in the age range, or they have the condition, or whatever, has an equal probability, and then we purely randomly pick them. A stratified random sample is slightly different in that we first divide the population into strata, and a fixed number of observations from each strata or subgroup are randomly selected from the sample. We usually do this when we want to make sure that we're able to say something about specific subpopulations. If there's a population that's relatively small relative to the whole, we may not have enough participants who are in that subpopulation if we don't stratify first. That would be one reason to do it. There could also be other reasons why we might stratify, but those are the two main ways in which we go about sampling. I won't go into all the bad ways we can do sampling, but convenience samples are an example of a really bad way to do a research study. This is just grabbing, not randomly, but just the most convenient people to participate in a study. The ones that are most easily collected, and it may end up not being representative of any specific population, and it makes statistical inference impossible. Our statistics don't even allow for the fact that we're not randomly sampling from the population. All we can really say is what we observed among the people that we talked to. So avoid those kinds of methods, and ideally, as you're doing research, you'll be part of a collaborative team that will help consider all the ways in which you can sample from a population. So inferential statistics, as I mentioned, is related to probability. And to talk about the relationship, we have to think about what probability actually is. You've probably heard the term probability before. The odds are that you have, but in terms of your understanding of probability and the laws of probability, we're going to just briefly cover some of those. Okay, so the inferential statistics uses the laws of probability to talk about ways the roles chance affect our results. Okay, the chance that we're thinking about is that which is introduced by sampling. If we have full data on an entire population, we would not need inferential statistics. Okay, because we're taking statistics from a sample to say something about a larger population. We sometimes use the term statistics loosely to mean any kind of summary of data, but really a statistic is summarizing from a sample to make an inference. So we use probabilities to determine how likely it is that we would be getting a certain estimate, a certain parameter estimate by chance alone. Okay? And a lot of statistics has to do with dealing with that uncertainty that we have around our estimates. Okay, so let's talk about probability. So the probability of some event occurring is defined as the number of ways an event can happen divided by the number of total possibilities of an event. That sounds a little screwy. We'll see how this works in a second. We express probabilities as proportions, okay? So an example would be, if we're talking about a coin, there's only one way heads can occur, right? There's one variant on the coin that is the heads, okay? The number of possibilities when we flip a coin is 2. So 1 out of 2 times we're going to get a heads. We could say the probability of getting a heads upon flipping a true fair coin would be 0.50 or a 50-50 chance, right? We all can think of that, right? So that's what I mean by chances that would occur, or number of ways that it can occur, and the number of possibilities, the number of variants on the thing that we're looking at. Okay. So we can also calculate probabilities based on something like how likely is that to happen twice in a row, the probability of consecutive events. So we call that probability of A then B. And the probability of A then B equals the multiplication of the probability of that event happening times the probability of the event happening again. Okay, so the probability of getting 2 heads consecutively, heads then heads, would be the probability of heads times the probability of getting heads. So 0.50 times 0.50 is 0.25. Okay, so one time, chances are 50%. 2 times in a row, chances are 25%. There's a 25% chance of getting 2 heads in a row. Likewise, there would be a 12.5% chance of getting 3 heads in a row. Simply 0.5 times 0.5 times 0.5. And if we were to continue multiplying, we'd find that we have less than a 1% chance of getting 7 heads in a row. So the question would be, if you got 20 heads in a row, would you believe that the coin was a fair coin? It could happen. It's just very, very unlikely. And as you went on to 21, 22, 23, then you'd have to believe that you did not have a true coin, or the person who's flipping the coin has a secret. Okay, so that's a fairly straightforward example. Well, thought of coin flips probably in the past in terms of probability. We even use it as a way of deciding who's going to get the ball or whatever in sports. But what about when there's multiple opportunities or multiple ways in which an event can occur? We're going to use another common example here of drawing a red card from a deck of cards. So out of a deck of cards, if you haven't used the deck of cards in a while, there are 26 red cards and 26 black cards. And so once again, we have 26 possible red cards out of a total population of 52 cards. And so the probability of obtaining a red card upon a random draw is 1 out of 2, or 0.50, same as flipping a coin. Okay, even though there's multiple opportunities and there's multiple ways in which it can occur, the probability is the same. So the probability of drawing a red card is equal to the proportion of red cards in the full deck of cards. So this is an important concept, is that the probability of selecting some particular individual, let's say of a certain group or with a certain characteristic, is equal to their probability or their proportion in the population. So statistical inference is the process of making conclusions about a population that is subject to chance due to sampling. And what we're really asking is, what we're observing in our data, is it just a fluke? Is it just how we happen to capture people in our study? And how do we know that it's not a fluke? Or how can we be reasonably sure that it's not just a fluke? So here we are using the laws of probability, and we graph them to create what's called a probability distribution. We're going to make a little bit of a leap here from coin flips to something a little more conceptual, but we're going to use those laws of probability to make statistical inferences. So we can analyze the probability of an event using a probability distribution. One way we can think about a probability distribution is as an area. So if we think about, let's say, a height distribution, how likely is it that if we were to randomly select someone from the population, that we would randomly select someone who's over 7 feet tall? Probably pretty unlikely, right? So they're going to fall in this tail end of the distribution. You're probably going to get somebody around 5'10", right? If you just plus or minus a few inches, right? So there's going to be more and more people who are in this, okay? So knowing the distribution, let's say, of heights, we can calculate what is the probability of selecting any particular observation. And we can display this in a probability curve as shown here. So this would be a theoretical distribution where you've got a symmetric distribution, okay? And all together, if you add up all those probabilities, it's going to equal 1. And the amount of area under the curve represents the proportion of that total curve or likelihood of the event occurring. So there's going to be a higher proportion of events occurring in the middle of this distribution and relatively fewer towards the tail ends. Okay? So depending on the type of measure that we're collecting, we can use these probability distributions to make inferences or to determine the probability of a specific event occurring. A probability density function is a probability distribution for continuous variables. So that's what we would use for continuous variables. There are other probability distributions for even for nominal variables, for dichotomous variables. And so when we talk about an interval or continuous variable, we're going to talk about a density function. So for example, a distribution of IQ scores for a population of 10,000 10-year-old children. Okay, so let's say we have access to IQ information on 10,000 10-year-old children. We know that the population mean is 100 and the standard deviation is 15. Now notice this is based on all children, not the sample of children. So a child with an IQ score of 130 has a z-score of 2.0. That means they're 2 times 15 points higher on the IQ scale. So the mean is 100, standard deviation is 15, so they'd have a z-score of 2.0. A z-score of 2.0 on a normal distribution curve here corresponds to an area of about 2.3% of this distribution. Okay, so given that mean and that median, that's all we need to plot this distribution curve once we know those values, and again, assuming a normal distribution. This means there's a 0.023 probability, or p equals 0.023, of randomly selecting a child with an IQ of 130 or higher. Again, just like I said, the probability of selecting someone with a high value on height randomly selecting someone who's that high on the IQ scale would be about 0.023%, or 2.3%. So if we were to sample 25 10-year-old children from the population, would the mean IQ score of that sample be exactly 100? Probably not. Probably not exactly 100. Sample means from a population tend to fluctuate from one sample to another because of sampling error. The sample mean might be, for example, 98.2 or 101.6, a little bit off from the true population mean. And we'll never really know how far we are from the true population mean, but we can develop confidence intervals around our estimate, okay? So it's not likely that we're going to exactly capture that, especially with a sample size of only 25. So if we kept drawing samples from a population, what would that distribution look like? What are the values that we would occur? Sometimes we get 99.9, sometimes we'll get a 95.5, sometimes we'll get something like a 90, even though the true population is 100. And those things that are more close to the mean are going to be at the center of the distribution, more likely to occur. Ones that are in the tails, let's say we somehow managed to calculate the mean was 140, and it was a truly random sample, that's really, really unlikely to occur. So we can start to talk about that as being in the tail of the sampling distribution, right? So the sampling distribution is based on all possible samples that we obtain from this, okay? So it's a theoretical distribution, not an actual distribution of values, which is a little hard to get our head around, but the idea is if we were to continuously draw samples from a population, what would that distribution look like? So this brings us to the calculation of the standard error of the mean. The standard error of the mean is the standard deviation of this theoretical sampling distribution that we were talking about. Again, this is of all the possible values that we would get for our sample mean, what is the standard deviation, so to speak, for that sampling distribution? Okay, so we can't calculate it directly, but we can't estimate it. So the standard error of the mean is how we take into account the level of uncertainty when we calculate a sample mean to estimate a population mean. The larger the SEM, or the standard error of the mean, the less likely it is that the sample mean is a good estimate of the population mean. The standard error of the mean is never known, but it can be estimated. So the standard error of the mean is the sample standard deviation divided by the square root of the sample size. So we calculate the standard deviation in our sample and then divide that by the square root of our sample size. Notice that the sample size is in the denominator. So given a certain amount of variability in our data set, the most determining factor here is going to be how many people are in our sample, because the standard deviation is not going to deviate that much from sample to sample. But if we have a bigger N, our SEM is going to get smaller. okay? Because and the sample size is in the denominator. If we have a relatively small sample, the value of the standard error of the mean is going to get wider and wider and wider, right? So the larger the sample size, the smaller the standard error of the mean, the more accurate the sample mean was likely to be. Okay. Now, if I lost some of you on this concept, this is where we're making the leap from descriptive statistics to inferential statistics. And this is really kind of eventually going to be kind of in the back of our mind as we calculate statistics, but it's important to understand that what we're estimating here is how likely is it that we're different from the true population value that we're trying to estimate. In this case, the mean, and we're calculating some bounds around that estimate, largely dependent on sample size. So an example is if we had a sample mean of 101 and a standard deviation of 10.5, we would then calculate an estimated standard error of the mean. 10.5 divided by the square root of 25 or divided by 5 would be 2.1. Okay. Well, what does that mean? Well, it's really hard to say in an absolute sense what that means. But if we were to have a larger sample size, let's say of 225 children, the standard error of the mean for that sample, and here the standard deviation is the same, is 0.7. So we have a standard error of the mean in one sample of 2.1, and we have for another one 0.7. The difference here, standard deviation is the same, the sample size has changed, and therefore the range in which we're saying that the true population falls is somewhat narrower in the larger population. So what do we do with the standard error of the mean? Well, we're able then to calculate a probability distribution based on that standard error of the mean. So with a sample IQ of 101, which is our estimated population mean, and a standard error of the mean of 2.1, we construct a distribution around the mean to estimate the likelihood of obtaining a sample mean within a given range. Okay, so how many values, if we know that the standard error of the mean is 2.1, if we construct a normal distribution curve around that, we can then say, where are 95% of the values likely to fall and what's going to fall outside that range. Okay, so once we know that, we can calculate that. So in this sample, the probability is about 0.95 or 95% that all sample IQ means for the population of a 10-year-old children would be no more than 2 standard deviations below and 2 standard deviations above the mean. That would give us values of 96.8 and 105.2. How do we know this? Well, from a standard normal distribution, that is the proportion that would fall in those two tails, 2.5% on the far left, 2.5% on the far right. That was roughly where we would be. We're not doing an exact calculation here. So with a sample, again, of 225, standard error of the mean of 0.7, the range would be between 99.6 and 102.4, based simply on looking at that distribution. If we had a larger sample, we'd have a greater precision of that estimate. The standard error of the mean would shrink, the tails would shrink, and we're going to have more precision around our estimate. We're moving on to one of the most important concepts in statistics, which is the central limit theorem. The central limit theorem is actually a mathematical formulation that says that the mean of a sampling distribution of the mean always equals the population mean. Basically, that if you were to continuously draw samples from a population, the mean of that sampling distribution would equal the population mean, okay? And we then have values tailing off from that. So the population mean values are normally distributed, so is the sampling distribution of the mean. Another important point is that when sample sizes are large enough, the sampling distributions are normally distributed even when the population values are not. Okay, so even when we're starting to sample something like a proportion where it's not normally distributed, we can assume that the values that we would get as estimates of the population would follow roughly a normal distribution. So as we get large enough samples, even a non-normal distribution, the sampling distribution of this theoretical sampling distribution will take on a normal distribution. So this is what allows us to use a normal curve or variations on a normal curve to construct probability distributions pretty much for anything that we can quantify. So a 95% confidence interval designates the range of values within which the population parameter has a 95% probability of falling. Again, if you think about a normal curve, those tails are going to represent about 2.5% each. So that means that when we say we're 95% confident, is that we're saying that it's somewhere in that distribution of values. And if we get larger sample sizes, that becomes narrower and narrower. The tails become smaller, much more towards the peak. With larger sample size, it's going to be out like this, and there's going to be more area under that curve. So when we construct a confidence interval, it really does depend on the sample size in addition to the variance of the variable that we're looking at. So we can calculate a confidence limit by getting an upper limit and a lower limit. And these are usually proportionate around our point estimate. In the case of the confidence interval around a mean, it would be proportionate at a specified probability level. And when the most commonly reported confidence intervals are 95% confidence intervals, you'll occasionally see 99% confidence intervals. Other confidence intervals are not reported by convention. There may be reasons to do other ones, but those are what we've agreed upon as a statistician community. And we'll talk more about kind of the history of why we've used the values that we've chosen. So calculating a confidence interval, we just need to know the following. We need to know the sample mean. We need to calculate the estimated standard error of the mean, which is going to be based on taking the standard deviation divided by the sample size, or the square root of the sample size. The value corresponding to the area from a theoretical distribution for the desired confidence interval. So for sample means, the appropriate theoretical distribution is the t distribution for small samples and the z distribution for larger samples. And in your book, you will see examples of a z distribution table and a t distribution table that will calculate for us or provide cutoff points for those tails of the distribution. A t distribution is very similar to a normal distribution. It's bell-shaped, it's symmetric. However, it starts off relatively flat peaked and more area in the tails. And as you get larger and larger samples, it becomes more peaked until it achieves what we'll call a standard normal distribution. And at a certain sample size, it only changes very little bit as we get larger and larger samples. It's usually in the first few increases in sample size. So a leap from 10 to 20 is a pretty big leap in sample size. A leap from 20 to 100 is a huge increase in sample size. But going from 100 to 200, it's definitely helping, but it gets incrementally smaller and smaller in terms of how it's going to affect the shape of that sampling distribution. And eventually, once we get large enough sample sizes, then we can just use what's called a z distribution, which is a standard normal distribution that we don't have to even think about the slight differences in the shape of that curve. So for small samples, the tails of the t distribution are fatter, wider. There's going to be more likelihood of having values out in those ends. And so we need to account for that using a series of distributions, which are called t distributions. So the formula for calculating 95% confidence interval around the mean, first we calculate the mean, plus or minus our t statistic that we want from that distribution, times the standard error of the mean. So in our earlier example, with an IQ score, mean of 101, standard error of the mean of 0.7, we'll look up a value from a table. Okay, there's a table in your book that has t values, and the value that we would get from that table would be 1.96. And actually for large samples, 1.96 would be what we would use as our t value or our z value for sample sizes of about roughly 200. Okay, so this is going to be a slightly better estimate than what we calculated before. We just had that like about 2 standard deviations from the mean. So 95% confidence interval precisely calculated would be 99.63 to 102.37. that means that there's a 95% probability that the true population mean falls somewhere between 99.63 and 102.37. Could it be outside those bounds? Yes, but it's a very, very, very unlikely, given that if we were to continually take samples from the population, getting something further away would be very, very unlikely. Okay? So I know we went a huge leap here in thinking about just calculating a number, living with it, reporting it out, and saying, hey, this is my number, and going to this inferential statistics where we're saying, okay, what are the bounds of certainty around this? How close to the truth are we with this? And we can use probability to develop these sampling distributions, particularly, let's say, a sample distribution of a mean, and calculate how likely we are to be off ever so little in each direction. It's really a powerful tool, and the fact that we have a little bit of control over how much error there is by sample size is really important. Again, assuming that we've randomly sampled from a population and we've done other things in terms of measurement and methodology that are appropriate to get those estimates. So that's our first discussion about inferential statistics. So this time we talked about confidence intervals. Next time we're also going to So confidence intervals are a big part of inferential statistics. What we're going to cover next time is hypothesis testing, which is also based on constructing these probability distributions and making some claims, let's say, about what's happening in the population, differences between two groups. That's going to be our main focus this week. And a lot of this is similar in that we are making inferences based on these probability distributions, as we'll see. So hang in there. This will start to make more sense as we get some practice. And again, this is really background to doing analysis. We won't be thinking about this consciously too often as we're performing actual statistical tests, but this is what's underlying statistics in terms of our calculations. So thanks for hanging in there. We'll talk again next time about hypothesis testing.